Okay, you all can see my screen. All of you can see my screen.
Yes, ma'am.
Okay, please, no one should put on the camera or the audio unless required. Okay, so just a second. So in the last two classes, we have been discussing the vector differential operators, the gradient and the divergence. And in our last class, we also discussed what is the physical significance of the divergence. And we saw that it basically represents the flux when there is a group of particles or lines of force or fluid, which again is a group of particles moving through a region, then the flux is the physical meaning of the divergence of the vector related to the movement of the particles. And for gradient, we saw that it is the directional derivative, and geometrically it gives you the normal to a given surface. Okay, so after these two differential operators, today we'll move on to the curl operator. Okay, so meanwhile you should start doing I hope you have started doing numericals related to gradient and divergence from Spigel's book. There are several problems that are worked out and that are given for you to work out, so you should go through them and try them out. So today we'll do curl of a vector. Now mathematically, if V is a differentiable vector field, the definition of the curl is this. Okay, so you write the expression of the grad operator as del x I cap plus del y j cap plus del z k cap, and you write the expression of the vector field v1 I cap plus v2 j cap plus v3 k cap, where v1, v2 and v3, the components are also functions of x, y and z. And you take a cross product of the operator with the vector, and writing down the determinant formula of the cross product, this is what we get. Someone's audio is on. Please mute yourself. Please mute your audio. If you don't have any question relevant to this, then please mute your audio. So evidently this is a vector. So operating the grad operator on a vector, last day we saw that taking the dot product, we had got a scalar, and it meant we are talking about the flux of the vector, which itself is a scalar. And today, taking the cross product of the operator with the vector, we are getting a vector. So we have to understand what this physically means. Mathematically, of course, this is the expression, but obviously you won't learn this up. If you are asked to find the curl of a vector, then you will write down the determinant and see what the curl is. Can someone immediately now tell me what is the curl of the position vector r? If you can do it mentally, or if you want to write it on a piece of paper and check what is the curl of the vector r, position vector r.
Zero.
Yes, 0. Very good. 0 with a vector. So answer will be null vector. Okay. Answer will be null vector. Obviously, you will not get the partial derivative of any one component with respect to that. All the components will mismatch. So answer is null vector, and we'll soon see why we are getting a null vector when we talk about the physical interpretation. By the way, Just like we saw that when you take the divergence of a vector, you can get either an answer which is greater than 0 or less than 0 or equal to 0. And when it is greater than 0, we say there is a source present. When it is less than 0, we say there is a sink present. And when it is equal to 0, we say the vector is solenoidal. Okay, we discussed this in our last class. Similarly, there is a special name when curl of a vector is 0. When the curl of a vector comes out to be 0, just like we now found that the curl of the position vector is 0, the vector field is called irrotational. It is called an irrotational vector. Okay. So now we'll discuss the physical significance of taking the curl of a vector and why it is called irrotational, what is the link of rotation with it, etc. So for doing that, let us consider a rigid body which is rotating with a constant angular velocity omega. Okay, consider a rigid body. It may be a cylinder, it may be a parallelepiped or a sphere or anything, even not a regularly shaped body, but it moves, it is rotating with a constant angular velocity omega. Constant angular velocity, remember the angular velocity is not variable. So the linear velocity, you know the formula that the linear velocity is given by v equal to omega cross r. Okay. So if you now take the curl of this linear velocity v, then basically we are taking the curl of omega cross r, since v is omega cross r. So we write the determinant for omega cross r. This is what we get. And then when we take the curl of this vector omega cross r, then we again write the second determinant for the curl, and this is the value that we get. So when you calculate this determinant, what you get as a result is 2 wx or omega x I cap plus omega y j cap plus omega z k cap. In other words, we get twice the angular velocity. Okay, you can do this by yourself. I have not written down the steps in between. You can do this and verify that this is the answer that we get. So what we are trying to see is that curl of linear velocity is giving us angular velocity, right? So angular velocity is equal to half of curl of v. Okay, so when we have a body which is moving with a linear velocity v, then we will get an angular velocity related to the body which is equal to half of curl of v. Okay, so this gives us a clue to the name curl. Okay, you know the meaning of curl. Curl means when do we say we have curled? When we say curl our fingers, or when you see curly hair. Okay, so there is a concept of rotation. So curl is also sometimes called rotation. Rotation of a vector instead of curl of a vector, but curl is the more common name that is used. So why this name curl or rotation is used, that concept comes from this result of this very simple problem that we discussed about. In this particular problem, the curl gave the angular velocity of rotation of the body, right? So if you know the velocity, the linear velocity, then you can take the curl of the linear velocity and you will get the angular velocity. Obviously, if the linear velocity is a constant, then taking its curl doesn't make sense because curl is a differential operator. So if a body is moving with a constant linear velocity, then it will not have any angular velocity. And that essentially is the physical interpretation of the curl. It is related to the rotational motion of a body, and rotation is possible only if the linear velocity is a variable term. Okay, so as from this simple example you can see that if the body which is moving with a velocity v, if that velocity v is a constant vector, then curl of v would be 0, and then you would not get any angular velocity related to it. So you would get an angular velocity only if the linear velocity is a variable. Okay. So for the flow of a fluid, for example, curl v at a point is a measure of the angular velocity of the fluid in the neighborhood of that point. Okay. Evidently, if curl v is 0, then the velocity v is irrotational in that particular region. This is why the curl is related to the rotational motion of a body. Okay, we'll take another. We'll sort of do a thought experiment from which this concept will become clearer. Okay, so what is the thought experiment? So to physically understand the situation, we'll consider different types of movement of water. Suppose a particular amount of water is moving, it can move in different kind of ways. So we'll now see what are the different kinds of movement that a water can undergo and how that can allow us to physically interpret the action of the curl operator. Okay. So for example, these parallel lines, suppose they represent the flow of water. Okay. So as you can understand, as you have done, I think, viscosity in your viscosity and surface tension, I think you have done these preliminary concepts of these topics in your +2 syllabus. And can someone tell me, can someone unmute and tell me what this kind of a motion is called? When a fluid moves such that its motion is represented by parallel lines, what is this kind of a motion called? Does anybody remember?
Ma'am, is it streamline?
Yes, exactly. Streamline motion. So this is a streamline flow of water. Here we are talking about water. So here we are considering a streamline flow. But as you can see, although it is a streamline flow, but there is no variation in the velocity. All the layers of water are moving with the same velocity. Correct? In this particular case. So if you now drop a small little plastic, wheel kind of a thing amid this flow, water is flowing in a streamline, parallel layers, layers parallel to each other, all flowing with the same velocity. Now suppose we drop a small, very light plastic wheel in the face of this flow. Then what will happen to this wheel? If the water is flowing very fast, then it will just carry away the wheel. We are not talking about that. We are considering a slow movement since it is streamline flow. But since there is no variation of the velocity vector along this vertical line, so basically, ideally, this wheel will remain stagnant, but of course it might undergo up and down vibration, but it will definitely not rotate. Okay, so placing a light toy wheel will not result in rotation of the wheel. Why? Because the velocity with which the different layers are moving is the same. Okay, v is constant, so curl v is 0, so there is no angular velocity related to this particular case. Okay, now consider again a streamlined motion. So this is also streamlined because all the layers are parallel to each other, but there is a velocity variation. All of you know that when water flows through a capillary tube, the outermost layer, that is the layer which is in contact with the wall of the tube, that remains at rest. Velocity there is 0, and the velocity at the axis which passes through the center of the tube is highest. So there is a velocity gradient present if you move from the center of the tube to either sides towards the wall of the tube. So there is a velocity gradient present. Velocity is not constant. It varies from layer to layer. Consecutive layers have different velocities. So now if you place a small plastic tube, small plastic wheel in the face of this flow, what will happen? Evidently, you can see that the force due to this flow of water on the two edges of this wheel are not same. It is higher on this side and lower on this side. And since the two forces are unequal, there will be a torque that acts on this wheel, which will make it rotate in a clockwise direction in this particular case. If the gradient would have been in the different direction, then it would rotate in the anti-clockwise direction. So in this case, since there is a velocity variation present, from our intuition, we can say that placing a light toy wheel will result in rotation of the wheel. So here there is variation of velocity. So curl V is not zero. So there is an angular motion present. There is a certain angular velocity, and that results in the rotation of this small toy wheel that is placed in the face of this motion. Now we consider a third case where motion is no longer in straight line, but the water is moving around a corner. So suppose there was a pipe like this, it came in, and then there was a corner so that it had to bend around the corner. So obviously there is a variation in velocity in all the layers of water that are moving around this corner. There is evidently there is variation in velocity, and therefore if you place this wheel now over here, it will definitely rotate because there is a torque acting on it. The force acting on its different edges are different, and therefore there will be a resultant torque which makes it move. In other words, the variation in velocity means that curl V is non-zero, and therefore that angular velocity will make the toy wheel move. Okay, you can picture this thing. Suppose you can think of a drain through which water is passing, and suddenly there is a bend, and you can evidently see movement of water around the corner, around the bend is definitely different than that along the straight pipes through which it was moving earlier. Please don't unmute yourself, whoever has unmuted. Okay, so it will result in rotation of the wheel. And finally, we talk about a vortex. Okay, this kind of movement, I am sure all of you have seen whirlpools in rivers or tubs. When there is a drainage in a pool or a tub, then when the water drains out, it forms a whirlpool. Whirlpools are also seen in rivers, sometimes in lakes. I'm sure all of you have seen such a whirlpool, and the movement of water in such a case is called a vortex. Okay, so all the layers of water are moving in circular motion about a central point, and they form a vortex, and evidently there is velocity variation. And now if you put this the toy of ours with which we have been experimenting from the beginning of this discussion, if you put it anywhere, be it a center, be it somewhere other than the center, it will definitely start rotating because there will be a resultant torque acting on it because of the difference in force acting on its different edges, and the wheel will start rotating. So curl V is not zero, which is why there is an angular velocity and which makes the wheel rotate. Okay, so basically by discussing these four cases, it should be clear to you now why curl of a particular vector is related to the rotational motion of the body, which is being represented, the movement of which is being represented by the vector. Okay, is it clear to all of you? Do you want me to explain it once again, or have you sort of understood what is the physical meaning of curl of a vector? If you want, I can repeat this once more. Is it more or less clear?
It's clear, ma'am.
Yes. So, and related to this, if a field is not irrotational, then it is called a vortex field. Okay, which sounds good because it is when there is, I mean, not an absolute vortex, but it is only when there is a change in the velocity that the vector will be rotational, not irrotational, and then it is called a vortex field. In fact, waves, if you've been to the ocean, if you've been to a sea beach, you must have noticed that waves are formed near the beach. Even if it's a large pond or a river, you can see that small waves are formed near the bank. And in case of the sea beach, large waves are formed near the ocean. If you have been on a cruise, or if you've been in the high sea on a ship, or if you watched movies, then you've definitely noticed that you don't get very large waves in the middle of the ocean or in the high sea unless there is a storm. Okay, so then when there is a storm and when there is bad weather, then it's the storm that is making the water move. But in general, when the weather is fine, you won't get very large waves when you are in high sea, whereas large waves are formed when you are near the shore. Why is that happening? Because the large mass of water that is coming towards the shore is basically getting a velocity gradient. Why? Because the shore does not, it does not drop uh, suddenly. There is a slope with which the ocean floor from the beach, uh, the landmass as it goes to the ocean floor, there is a certain slope. It's not a vertical drop. So when the landmass is from the sea bed, or rather from the what you may call it sea level, as it goes down to the sea bed, the ocean floor, it is a slope. Okay, sometimes steep, sometimes not so steep. So the water that is coming and hitting the shore, the lowermost layer the lowermost layer hits is the first one to hit, and the topmost layer is the last one to hit the beach. And so there is a velocity gradient which makes the water rotate. Okay, and that rotation causes the waves to form, which is why large waves are always formed near the shore and never in the middle of the ocean. So it is the gradient of the velocity, the variation of the velocity, that causes the angular motion of the water and causes the water to rotate in the form of large waves. Okay, so this is the concept of curl. I won't do problems on curl because we have already done some problems of gradient and divergence, and so you can by now you should know how to work out these problems, and I've given you the formula. There is not much to say, or not much variation in the problems that are given to do when you are taking the curl of a vector. You are given directly, you can use the formula of the determinant form of the curl directly. Of course, when we do curvilinear coordinates, then we'll need to know how to find out the curl in different coordinate systems. So for the time being, this would suffice. And so this more or less covers gradient, divergence, and curl. After this, you can, as I told you, that gradient, divergence, and curl are the primary vector differential operators. Of course,